Hi, so this is the topic of our project. It is the Damp Cityscape Exploring the Urban Heat Island Effect Through Humidity by Kennedy and Daniel. I'm Daniel. You ever notice the heap of steam that lingers after a hot shower and keeps the bathroom warm even after the shower's over? Well, turns out that the tiny droplets that create humidity can hold onto heat. So as we explore the urban heat island effect and its effects on temperature, we cannot neglect the role of another key heat determiner, which is humidity. That's what our case study is on. So we chose our location as Central Florida because Central Florida is a key and notoriously humid environment as long as and it also has a very urban environment as well. So it's a great combination for our case study, which is to study humidity and its effect on the urban heat island effect. So I'm going to pass it on to Kennedy.
That being said, our study aims at answering the following two questions. How have humidity levels within the urban areas changed over the last decade, and how has it affected the urban heat island effect? The time frame will be between 2012 and 2022, and I will be in charge of answering this question. My partner Daniel will answer how does soil moisture affect humidity levels, and how does this affect the urban heat island effect? His time frame is between 2015 and 2023. In terms of background information, one crucial study we found told us that there's a negative correlation between relative humidity and urban heat island intensity. In other words, as relative humidity increases, the urban heat island intensity weakens. The scatter plot depicted here actually reveals that larger magnitudes of urban heat island intensity occur during conditions of high relative humidity, while the highest urban heat island intensity occurred during hot afternoons when the air was much less humid. A second source we analyzed told us that the urban heat island effect can be explained by changes in the efficiency of convection, which in other words is the transferring of heat between land surface and atmosphere, which, funnily enough, humidity can help conduct through water vapor. And essentially, this implies that humidity can help us suppress the urban heat island effect as it allows for convection to actually occur. Finally, a third source we looked at explained that there's a synergistic relationship between urban heat island and urban moisture island, which, similar to urban heat island, is related to moisture and implies that higher moisture levels are found in areas of higher vegetations or what usually are more rural areas. And it explains that although plants do help with the urban heat island effect by allowing for convection to happen through water vapor and evapotranspiration and other plant processes, it does increase the urban moisture island as a result. In terms of what we did to conduct this study, I sourced my data from Florida Climate Center's monthly climate reports, specifically for my air temperature data, and sourced my humidity data from Weather Underground's monthly reports. I then took this data and calculated monthly averages in Google Sheets and created an ArcGIS slider map using this data showing the last 10 years. Then I created a time series graph and regression graph for both relative humidity and temperature. And finally, my partner Daniel made use of SMAP data to create regression graphs comparing soil moisture and humidity, soil moisture and land surface temperature, humidity and land surface temperature, and finally, a Google Earth Engine layered map to depict all of these data sets. It's also important to note that he sourced both the land surface temperature data from Landsat satellite data on Google Earth Engine, as well as humidity data from Google Earth Engine. Moving on to my analysis, as you can see on the left, this is the average relative humidity over the last 10 years, and it does seem to be fluctuating a lot, but seems to be on somewhat of a decline since 2017. It oddly peaked at 89% in June of 2017, which could be explained by some sort of climate event that occurred in Orlando, Florida. However, it is important to note that drier air usually means higher temperatures, as we've established. So the expectation is for there to be higher temperatures around this time as well. And that is somewhat what we see. Overall, temperature seems to stay pretty consistent. It stays above 75 degrees Fahrenheit and actually peaked in July 2016, around the same time that relative humidity peaked, which is certainly a good sign. And it has been slowly increasing, very slowly, since June of 2017, which does support the relationship we established earlier. Moving on to my time series graphs and regression graphs, as you can see on the left, here is my regression graph comparing the average temperature and relative humidity. And the trend line seems to be steadily going down, which I did not expect. It basically goes against everything we learned up until this point. And it pretty much tells us that as relative humidity increases, the temperature actually decreases. That being said, we should consider that the R2 value is 0.278. And to clarify, the R2 value tells us the reliability or the strength of the trend line in showing us the relationship between both data sets. And given that it's a scale between 0 and 1, the reliability of this trend line isn't very high. Moving on to my time series graph, as you can see in the boxed area, we get an exact point that explicitly shows us a point where average temperature was increasing and relative humidity was decreasing, and later on, relative humidity was increasing while average temperature was decreasing, which again supports the relationship we established before. It is important to note that given that temperature has stayed pretty consistent across all 10 years, it kind of seems like it's indifferent to humidity, almost like it doesn't really care about it, doesn't really isn't really affected by it, which does put into question what we know. Finally, here are the slider map visuals that I created. As you can see on the upper one, overall the humidity levels seem to be decreasing since 2017, as established earlier, while temperature has been gradually increasing. But prior to then, temperature was steadily increasing, but hit a plateau in 2016, and after that there was a large spike, and then decreases to a more reasonable amount. Thank God. And since then, humidity has been mildly random until 2017. And most importantly, if you view both maps in relation to each other, you can see that at the start, humidity always seems to be smaller than temperature, which does help enforce the relationship we have established. And all the other data sets and graphs and observations we made previously.
So to start off, here's some map layer visuals. You can see the soil moisture, the humidity, the land surface temperature on Google Earth Engine. So here is my data on what happened. So it shows that everything's kind of linear, and you expect the graph to actually just fluctuate, but it doesn't because it's a linear regression. So everything kind of impacts each other. If the soil moisture goes up, then the humidity goes goes up. If the land surface temperature goes up, then the humidity goes down. As a result, the soil moisture goes down. So you would expect everything to fluctuate, but it doesn't because if everything remains linear, then everything else remains linear as well. And this is backed up by the time series graph that I'll be showing you right now. As you can see, the land surface temperature fluctuates from a time series. This is due because of that that the land surface temperature actually depends on the season because everything correlates to each other. For example, if it was a cold season, then that means the land surface temperature will go down, increasing and if you look at the graph, that means the overall temperature for soil moisture and humidity will go up and raise. However, the land surface temperature and humidity are inversely proportional, just like a math equation. That is why it fluctuates in this time series chart. It just keeps going up and down because it depends on what season it is. So here are our resources, and thank you for listening.